Imagine looking out at the universe and realizing that nearly everything we can observe is only a fraction of what's really there. The rest? It's hidden, unseen, unmeasurable directly, and deeply mysterious. This invisible part of the cosmos, known as dark matter, makes up roughly 27% of the universe. Today, we'll dive into one of the most mind-bending topics in science and explore what we know and don't know about dark matter. To understand why dark matter matters, we need to start with some fundamental questions. Imagine walking through a room filled with hidden objects you can't see but can feel their effects. Similarly, scientists discovered that the gravitational effects in the universe don't add up if we only account for visible matter. Something else must be there, something that doesn't emit or absorb light and doesn't interact with ordinary matter in any known way. The first clues pointing to dark matter came in the 1930s, when Swiss astronomer Fritz Zwicky observed the Coma cluster, a group of galaxies bound together. Zwicky noticed that the galaxies were moving much faster than the visible matter in the cluster could account for. This led him to propose the idea of a missing mass, which he suggested might be some invisible substance exerting gravitational influence. Then, in the 1970s, astronomer Vera Rubin provided even more compelling evidence. Studying the Andromeda galaxy, Rubin found that stars on the outskirts were orbiting just as fast as those near the center, defying expectations based on Newtonian physics. The only explanation: a massive, unseen force was holding them together. So what makes dark matter different from ordinary matter? Unlike stars, gas, or dust, dark matter doesn't emit or absorb light, making it invisible to telescopes. It also doesn't interact with other matter in the traditional ways we know, like through electromagnetic forces, which means it doesn't form atoms or molecules. But it does have mass, which allows it to create a gravitational pull. This gravitational pull is how we detect it, by observing its effects on visible matter. In fact, scientists have mapped dark matter in entire galaxies by measuring how it warps and bends light through gravitational lensing, giving us an indirect view of its distribution. Studying dark matter isn't easy, given that it doesn't interact with light or typical detectors. Researchers use various indirect and direct methods to find traces of it. Indirect detection looks for particles and radiation that may be byproducts of dark matter interactions, such as gamma rays or neutrinos, while direct detection involves highly sensitive detectors set deep underground to shield from cosmic rays. These detectors, often placed in remote caves or beneath mountains, are hoping to catch rare instances of dark matter particles interacting with ordinary matter. But so far, no definitive detection has been made. Each year, new detectors are developed with even more sensitivity. Dark matter plays a crucial role in the structure and evolution of the universe. Think of it as a cosmic scaffolding on which galaxies and galaxy clusters form. Without dark matter, it's unlikely galaxies would have the gravitational force to stay together over billions of years. One way to understand this is to look at the cosmic web, a vast structure of dark matter that stretches across the universe. The filaments and nodes of this web are where galaxies and clusters form, held together by dark matter's invisible gravitational influence. Over the years, scientists have developed many theories to explain what dark matter could be. Two leading candidates are WIMPs, or weakly interacting massive particles, and axions. WIMPs are theoretical particles that would be heavy and only interact through gravity and weak forces, which would explain their elusive nature. Axions, on the other hand, are extremely light particles that could collectively create a significant mass in the universe. Another theory even proposes that dark matter might be made of black holes formed in the early universe, called primordial black holes, though evidence is still inconclusive. In recent years, experiments like those at CERN have tested particle collision data for signs of dark matter. Projects like the Alpha Magnetic Spectrometer on the International Space Station are scanning cosmic rays to look for dark matter signatures. Though we haven't yet detected a dark matter particle, each experiment brings us closer, refining what dark matter isn't, if not what it is. Interestingly, dark matter isn't the only mystery in the universe. Dark energy, which makes up about 68% of the universe, is a force pushing galaxies apart, causing the universe to expand faster over time. Though dark matter and dark energy are often mentioned together, they are thought to be very different phenomena. Dark matter's role is gravitational. It pulls things together, while dark energy pushes them apart. Yet, understanding one could help unravel the other, providing insight into the ultimate fate of the universe. Understanding dark matter could lead to breakthroughs in physics itself. If dark matter particles are discovered, it may mean the existence of new forces beyond the standard model of particle physics. Some theories even suggest that dark matter could be related to other dimensions, opening up fascinating possibilities about the true nature of reality. As technology advances, scientists hope to create more sensitive detectors and space-based observatories to continue the search for dark matter. The detection of a dark matter particle, or even just confirmation of its nature, would be a monumental achievement, changing our understanding of the universe. But for now, dark matter remains one of the greatest mysteries of our time. While it's invisible, it's one of the most crucial pieces of the cosmic puzzle, holding galaxies together and guiding the universe's evolution. Join us as we continue to explore the universe piece by piece, mystery by mystery. Until then, the question remains, what is dark matter and when will we finally see the invisible?